Hi, everyone. So we're going to continue today to be able to get estimates of hydraulic conductivity and transmissivity, as well as storativity of our aquifer systems, specifically confined systems. And we're going to work on two equations or two methods that we can do this under transient conditions. So let's move on. So the first one is we're going to be working with what's called the Theis method or equation. And essentially what we're looking at is drawdown under the drawdown is occurring over time, right? So we're measuring over time a change in heads in these systems. We're having, again, a series of assumptions. So homogeneity, isotropy, fully penetrating, fully screened wells, right? So going across the entire confined system for both the pumping well and observation wells as well. We have infinite resources for the water in terms of recharge, and the well is 100% efficient, meaning that it doesn't store extra water within the system. So this equation we've seen before, it's just the two-dimensional transient groundwater flow equation. In this instance, right, we're using the idea of transmissivity and storativity here and thinking about over time as head levels change, right? And their relationship to storativity is related to the transmissivity and the way that water levels change in the X and the Y direction. But when we think about pumping tests, right, we're thinking about this, especially in homogeneous isotropic systems, can be represented by a circle or the radius of a system. And so instead we can use radial coordinates. And we can plug those radial coordinates in because X and Y would be relatively the same in this system. And we can come up with this solution here. Now, when we begin to think about these drawdowns, there are some conditions that we need to know about that are being assumed. Our first is our initial condition. And our initial condition says that before we start pumping, so at time zero, anywhere we go in terms of our radial directions, our initial head, right, HO, is here. So that's the first one. And then our boundary conditions say that some distance into infinity, and infinity would be out here in this instance, at some distance out into infinity, our water level goes back to our original condition, HO, here. In addition to that, the only other thing that we are saying in this condition here is as this test is taking place, this radius and the change in water levels as you move through this radius here are related to a constant amount of pumping Q. So that's all we're saying. And that they're related to that throughout time. All right. So when we begin to solve this and we begin to move outward from our system, we can move towards this kind of basically infinitesimal direction in our radius, right? As we're approaching our initial condition out there. And as we're doing that, we can come up with basically a value that helps us to solve at every one of those positions as we move out. And this value is just is a non-dimensional number that we have in the system here. And it's equal to our R squared times our storativity divided by 4 times our transmissivity times time. And now we take this value and we actually plug it in we can solve for it at any given place that we would like to. Now, instead of making that solution and then adding them up all together over and over again, what we can do is instead we can use something that's called a well function. So we can say, okay, our drawdown is equal to our discharge divided by 4 pi r times our transmissivity times this well function. And that simplifies this idea of moving out towards infinity in terms of our radius of our system and how it's behaving. And we can say, okay, we're going to use this well function and we're going to solve this well function based on, again, our radius, our storativity, transmissivity, and time. And so you can see here what I mean by that. So we're going to continue to solve and solve and solve. But instead of making the solutions, we can instead use a table. We can use table 9.2 to take a look at what this looks like. And so here are our well function values. And so we read our well function values from in here, and we use this table to determine which ones we want. So we have 1 through 9 at the top. We have 1 through times 10 to the minus 15, right? So inevitably, we're getting much smaller as we go down this way. And then the value of which we're getting much smaller is rounding to kind of the nearest whole number-ish that we have. So for example, if we had 0.012, right, we would say 0.012. Okay, so this is 1, this is 0.1, this is 0.01, and 0.012 would be closest to this value that we have right here. Now, the USGS, of course, because they have different units, and those units convert between both gallons, minutes, feet, and days, as you see down here, the values we may have before our well function and the values we may use within our U value may change. But inevitably, these are just conversion factors that get us to a place where we can make the solution itself. So in order to do this, we have our well function, right? Those are the values that we have for anything for any value of U that we're using. And then we have 1 over U, right? So that's what we have down here plotted in this instance. So as we change this to 1 over U, this is what our well units would change. And we call this the type curve. And these axes, if you can see here, this is a log axis here and a log axis here. We then go ahead and we plot our data. So when we're doing this test, what we're looking at is the drawdown versus time. And so we go ahead and we've collected this data. And again, now we have our time on our x-axis and we have our drawdown in this instance in meters on our y-axis. And again, it's a log-log scale, so looking very similar. Our third point is that we superimpose the two curves on top of each other. And the critical component here is when we do this when we superimpose one on top of the other, our axes here are parallel. So these x-axes are parallel and these y-axes are parallel. And you move this one of the two graphs around until they line up, right? Until you get the best kind of fit that you can get based on this idea of them staying parallel in these systems. Then you can select any match point. And so oftentimes, folks will say, use a match point of 1 and 1 over U, which is equal to maybe something like 1 in our instance too. Or something of that general kind of consensus. So just trying to pick a specific match point. So in this instance, that's kind of what we're taking a look at here. But the match point could be anything that we're interested in examining. So in this instance from your book, your match point is actually U1 with a well function of 1. So it can be variable in these instances. But the idea here is to go back and to say, once you've created this match point and these are sitting within them, you're just going to go back ahead and you're going to read off where that line is going to be crossing our drawdown and our time. So in this instance, when it crosses our drawdown, we take a look and that's about 0.78 meters or so. I would almost guess 0.8, like from the blurriness of this figure. And we see that here. And again, when we draw the line down here, on this one here, we see that it's about 22 seconds. So that gives us some ideas of how we can go about getting these values. So then we're going to take our S and our T values, and we're going to go ahead and solve our system. So we can begin first by calculating our T. So we know what our U value is. We know what our well function value is. We know what our S is because we were just able to read it off the matching curve that we had. We know our Q because we've been pumping, and we have then 4 pi. So we're thinking about our radial directions, right? So then once we have our transmissivity in this value, then we can go ahead and we can put our transmissivity, our time, our U value, our R squared value, and 4, and we can come up with our storativity value. Now, when U is really small, we can simplify the equation. And we can simplify the equation in these two ways. We can say that the change in the drawdown, or S2 minus S1, is equal to 2.3 times our Q divided by 4 pi T with a log of our time 2 and time 1. So drawdown at S, drawdown at time 2, drawdown at S1. And then we can say that our transmissivity is just equal to, therefore, our 2.3 Q times 4 pi times the change in our drawdown, our total overall drawdown. So when we go ahead and we think about creating these kinds of plots, we actually, this assumption of, being able to say, well, the U value is small, and so we can use a series of other equations to make these calculations, is actually, this assumption is called the Cooper-Jacob assumption or method. Mm-hmm. And so when we approach this one, what we do is we draw our drawdown, or we plot our drawdown. So you see our drawdown is on the x-axis. We plot our time, that's on our y-axis. Our drawdown's on our x-axis. We use semi-log paper. So you can see that the log is increasing in time, but we are unlogged or linear on our y-axis here, or arithmetic, right? So then we create a line. So we plot our data up here, and then our goal is to create the straightest line that we can. And oftentimes that means actually ignoring some of the very initial points that we may have had. Then as we move on, we choose 2 times, which should be separated by a log cycle. So in this instance, we're going to choose the times of 100 and 1000 in this instance. And when we choose 100 and 1000, we're going to go ahead and read off what is our S1 and what is our S2 in these values. So we can go ahead and say our S2 minus our S1 is our change in S that we have here. In this instance, we will know what our Q is, and we can go ahead and solve for our transmissivity. Then we can go ahead and we can say, well, we need to find as well kind of this initial time so that we can get back to our storativity. Now, in order to understand what this initial time is, we have to look back at the line that we drew. And this is where our drawdown is going to be 0, right? Because it's the intercept, or with the x-axis. So we're going to go ahead and take a look down at that. And what we see when we take a look back here is if we draw a straight line down and we see where we cross the x-axis in this point, right? We have here, it's going to be actually our drawdown is at t0, right? At time 0, when we have no drawdown that's taking place, it was actually 0.34 minutes when we still had 0 drawdown. So we go ahead and we plug that value into here. We have our transmissivity from up here. We know our R squared, that'll be a given, and you can go ahead and solve for your storativity.